Hi everyone, in this video I'm going to show you how to calculate the electric field of a uniformly charged rod. Let's get to it. Okay, so the first thing you want to do is draw the rod. It's just going to be a straight line. And it's going to have a total charge of capital Q, and it's going to have a length of capital L. Now, let's say we're interested in finding the electric field at some point in space. Call it x, y, z. And now what I do is I choose a random point on this rod. I'm going to say this one right here. I'm going to call it x prime, y prime, z prime. Now, the electric field of the charge at x prime, y prime, z prime is going to be dE equals 1 over 4 pi epsilon 0 times dq over r squared r hat. Now, the script r here that I've written is the distance from x prime, y prime, z prime all the way to x, y, z. And dq is the charge located at this point here. And in order to get the total electric field E at x, y, z, I have to integrate all along the rod here. So this is going to be the integral of dE. And that's just going to be 1 over 4 pi epsilon 0 dq over r squared times r hat. Now, in order to make the integration as simple as possible, I'm going to choose the coordinate system so that the origin is at this at the left tip here, and the vertical axis is going to be z0. The horizontal axis is going to be x0, and the axis going into the paper here is going to be y0. Now, the reason I write zeros here on the axes is just to distinguish the axes from the points that I've drawn already: x, y, z, and x prime, y prime, z prime. It's just a formality, if you will. And so, using this this coordinate system, I can now express dq in terms So this here is going to be 1 over 4 pi epsilon 0. If I write dq in terms of a geometrical quantity, the bar lies on the x0 axis. So it's going to be lambda. This is the charge density at x prime, y prime, z prime. But it's just a constant, so it'll be pulled out in front of the integral. This is times ds, the arc length, but because I've chosen it to be on the x0 axis, this is going to be dx prime. And over r squared, and r hat, that is the vector r over its magnitude r, like that. And as I said, the charge density is constant, so I'll pull it out in front. So this is lambda over 4 pi epsilon 0 integral. Oh, and also the limits of integration. So this charge bar, the smallest value of x is going to be, of x0 is going to be 0, and the largest value is L. So these are my limits of integration. So this is from 0 to L, 0 to L, and now dx prime over, this is going to be r cubed times the vector r. And because I've chosen this coordinate system as I have, the point here becomes x prime 0, 0, because on the x0 axis, the y and z are y prime and z prime are 0. Okay, so the next step is to write out what the distance is. So this here is going to be, this here is going to be lambda over 4 pi epsilon 0, 0 to L dx prime over. Now the distance here is going to be x minus x prime. We simply subtract the components and square it. So x minus x prime squared plus y minus 0 squared plus z minus 0 squared, and we cube that. And the vector r. So the script vector is the position vector that goes from x prime y prime z prime to x y z. So we do the vector x y z, and we subtract the vector that we're coming from. So so it's going to be x minus x prime y minus 0 z minus 0. So what we have here is the integral of a vector, and to integrate a vector, we integrate its components. So this is lambda over 4 pi epsilon 0. Now the first component is going to be integral from 0 to L. In the numerator I have x minus x prime. On the bottom I have, this is going to be, I almost forgot. Because r is a distance, this is actually, I forgot, there's a square root here. So, so this is going to be x minus x prime squared plus y squared plus z squared. And this is going to be to the 3/2 power. And this is in dx prime. That's the first component. And now the second component, integral 0 to L. This is y over the same denominator. I'm just going to copy and paste it to save time here. There we go. And the third component, integral 0 to L, z over, and the same denominator. Oh, I forgot the, this here is going to be dx prime and dx prime. Okay, so that is, so this, so the integral of a vector has become the vector of 3 integrals in the components. So now because our integration variable x prime appears under a root and is squared, we have to use trig substitution, my favorite method. Right, so in all these integrals here, I'm going to make the substitution, the trig substitution. X minus x prime, this is going to be equal to square root of whatever this is. So that's just going to be square root y squared plus z squared. And because this is addition, this is going to be, I'm going to use tan theta prime. Now, x is just a constant, so if I differentiate both sides, I get negative dx prime. And then this is equal to square root y squared plus z squared times secant squared theta prime d theta prime. So so again, I'm making the substitution in all 3 of these integrals here. Oh, and y and z are constants, so I'll bring them out in front of the integral as well. So this is equal to 1, oh, not 1, that's lambda. lambda over 4 pi epsilon 0 integral. So x minus x prime, that's going to be all of this here. So that's going to be, so in the numerator, I'm going to have square root y squared plus z squared times tan theta prime. And I have a dx prime as well. So that is going to be, it's going to be the negative of this. So it's going to be times negative square root y squared plus z squared, secant squared theta prime, d theta prime. And in the, so I should say that I'm just going to work out all the algebra here. So x minus x prime squared, this will be y squared plus z squared times tangent squared theta prime. And so that means that x minus x prime squared plus y squared plus z squared, that's what I have here in the denominator. I'm going to have this will be y squared plus z squared times tangent squared theta prime plus 1, which is going to be y squared plus z squared secant squared theta prime. So this is what I'm going to have in the denominator. So y squared plus z squared secant squared theta to the power of 3/2. Just double check that. Yes, okay. And it's going to be, the second and third components are going to be similar. So again, I'm going to bring the y out in front so that this is integral of negative square root y squared plus z squared secant squared theta prime d theta prime over y squared plus z squared secant squared theta to the 3/2 and z times the integral of the same thing. So by making this trig substitution here, we have to change not only the integrand, but also the limits of integration. So here, previously, x prime ran from 0 to L. Now, if we plug in 0 into this defining equation, if we plug in x prime equals 0, this is going to become x equals square root y squared plus z squared tangent theta prime. Now, if we solve for theta prime, this is going to be, I'm going to have, for 0, I'm going to have inverse tangent of x over square root y squared plus z squared. And if I plug in L for x prime into this equation here, it's going to be, this is going to be x minus L equals square root y squared plus z squared tangent theta prime. So in the upper limit of integration, I'm going to have inverse tangent x minus L over square root y squared plus z squared. Okay, And I'm just going to repeat these limits here. And on top I have inverse tangent x minus L over square root y squared plus z squared. And the same for the third component. All right. So now the next order of business is to simplify all of this. So we have on the outside lambda over 4 pi epsilon 0. So this square root y squared plus z squared times the same thing will give us y squared plus z squared, which is what we have on the, oh, hang on a second. So on the bottom, it's raised to the power of 3/2. So on the bottom here, it's y squared plus z squared to the power of 3/2. So I'm just going to have integral. And on the bottom here, it's going to be square root y squared plus z squared. And now I'm going to have secant cubed theta. And secant squared divided by secant cubed is just going to be 1 over secant theta prime. 1 over secant theta prime is going to be cosine. And cosine theta prime times tangent theta prime, that's just going to be sine theta prime. Now the second component. So I forgot the minus sign. So there is a minus sign here. So I'm just going to pull that out in front. And actually, there are minus signs in all of these. So I'll just bring it in front of the whole vector here. Okay. So the second component. So this here is going to be y squared plus z squared to the power of 3/2. So on the bottom here, I'm going to have y squared plus z squared. And this is going to be secant squared over secant cubed. That's just going to be 1 over secant theta. Oh, this should be theta prime. My mistake. So 1 over secant theta prime is going to be cosine of theta prime. And we have the same thing here. So integral and cosine theta prime over, this is y squared plus z squared d theta prime. And I'm just going to have all of these the same limits here. Okay. So this quantity here, y squared plus z squared, is a constant, so I can pull it out in front. So this is negative lambda over 4 pi epsilon 0. And now the antiderivative, so this is going to be 1 over square root y squared plus z squared. Now the antiderivative of sine theta is negative cosine. So negative, and then this is going to be cosine of inverse tangent x minus L over square root y squared plus c squared. And now minus the cosine of the lower limit. Cosine of inverse tangent x over square root y squared plus c squared. And I'm going to have, let's see, this is going to be y over y squared plus z squared. And the antiderivative of cosine is just sine, so this is going to be sine of the inverse tangent of x minus L over square root y squared plus z squared. And now minus sine of the inverse tangent of x over square root y squared plus z squared. And it's going to be very similar to, the third component is going to be the same, but with a z in the numerator because of right here. So that's going to be z over y squared plus z squared. And I'm just going to copy and paste all of this. Okay, so now the next thing we have to do is to simplify is to determine what the cosine and the sine are of this of these two angles here, and we do that from the definition. What we started with this x minus x prime equals square root y squared plus c squared times tan theta prime. So the tangent of theta prime equals x minus x prime over square root y squared plus c squared. I have to draw the implied right triangle. So if I just draw this out here, that's not very, that's a little bit better. So this is a right triangle, and I'm going to call theta prime this angle. I'm going to call this angle theta prime, and tangent is going to be the opposite. So that's x minus x prime over adjacent. So that's going to be this one right here. And now I have to use the Pythagorean theorem to determine the hypotenuse. So this here is going to be square root of x minus x prime squared plus y squared plus z squared. Yeah, that seems fine. So the cosine is going to be the adjacent over the hypotenuse here. And in place of x prime, I'm going to put L for this for the first term here. And for the second term, I'm going to put x prime equals 0. So this is equal to negatives lambda over 4 pi epsilon 0, negative 1 over square root y squared plus z squared. All right, so this is square root y squared plus z squared over the hypotenuse is going to be, okay, x minus L squared plus y squared plus z squared. And now minus, it's going to be the same thing, y squared plus z squared over but now I'm going to have 0 in place of L. So that's just going to be square root x squared plus y squared plus z squared. So this is my the first component. Second component is going to be y over y squared plus z squared. All right, so now I have to take the sine of the angle. So if I look back here at my right triangle, the sine is going to be the opposite, so x minus x prime over the hypotenuse. So it's going to be x minus either L or 0. So the first term here is going to be x minus L over this term right here, and minus, this is just going to be x over x over all of this. Okay. And the third component is going to be the same thing, but with a z over y squared plus z squared. All right, so now the question is, can we simplify this? So we can distribute the 1 over square root. So if I distribute both the minus sign and the all right, so this is going to be lambda over 4 pi epsilon 0. And now this is going to be 1 over all of this here, and now minus 1 over all of this. So that's the first term, the first component. And I distributed the minus sign, so I have to be careful. So this is just going to be y over y squared plus z squared. And it's going to be pretty much the same thing, but L minus x over oh, I realized I just made a mistake. So instead of L here, this is going to be 0. And this here is going to be 0 because this is minus 0. So these two should be the same. So right, so L minus x over all of this here. And now plus x over square root x squared plus y squared plus z squared. And it'll be the same for the third component. So this will be z over y squared plus z squared, and I'll have the same thing in square brackets. So yeah, this is the electric field at xyz. You can write lambda as the total charge over the total length, Q over L. So this would be your final answer, assuming I didn't make any other mistakes.